Welcome to section 2.1, examining numerical data. So topics to take note on for this section are measures of center and spread. And so that's going to be examples of that are going to be like mean, median, standard deviation, IQR. That's not a complete list. We'll get to that in a second. Then we're going to look at numerical graphs, numerical graphics, so ways of visualizing numerical information. So scatter plots, dot plots, histograms, box plots. And then we're going to look at descriptions of distributions. So it's going to be some keywords will be unimodal, bimodal, multimodal, symmetric, left skewed, and right skewed. Okay. So that's what we should be taking notes on. Let's begin. Here, let's go to this Gapminder site, if it still works. I hope it does. Okay. All right, so we're looking at life expectancy and income. And then we've got different countries. So, so United States is right there. And so, and then the size of the bubble is population. So let's play. And then as the years go by, got Europe and Northern Asia with the yellow, Middle East and Southeast Asia with red. And then things are moving around. Things are moving forward. Income and life expectancy are increasing across the globe. That brings us to 2018 when this graphic stopped. So that's different from what I had on the slide. It's more interesting, in fact. So in my case, the thing we looked at was income and life expectancy, and that was that those did appear to be associated. In that case, it was positively associated, whereas when I was, the slide has fertility and life expectancy, which is negatively associated. Yeah. Sorry, I feel like I have to sneeze, but now it's going away. All right. So that's a scatter plot. A scatter plot is great when you have two numerical variables. And you can make a third numerical variable could be time. You can like make a move around. All right. Something simpler is a dot plot. So a dot plot is when you have one numerical variable and you just want to show like where are things distributed around with those numbers. So this is an example of a dot plot with like semi-transparent dots, so you can see a little bit where they're grouping. And so how would we describe the GPA of this GPA data? Well, the GPA data is between 2.5 and 4. It seems to be centered somewhere around 3.5. It's hard to tell here. And it's spread out more on the left than it is on the right. When we'll learn a word for describing that in a second. So one example of something how to describe this distribution is that the mean is 3.59. Okay, so it's the center. So if imagine if all of these dots were on a teeter-totter, then the mean would be where they balance. Okay, so the mean gives things that are further away change the balance more. Whereas, so mean, the formula for the mean is adding up all things. In this case, say you have n things, x1, x2, all the way to xn, and then divide by n, which is the number of things you have. And then we will always use, this is terminology we will use for the rest of the course. We will always use the well, I gotta get the marker, the pen set up here. We will always use the X bar notation for it being the mean. So if I say my variable is X, then I will use X bar to be the average. And if my variable is Y, then I'll use Y with the bar over it to be the average. And if my variable is Y, I would say the different things would be like Y1, Y2, Y3. Okay. So then we'll also use, there's the population mean, which we often don't know. So X bar is the mean that we do know, the sample mean. And then this letter right here, this is the Greek letter mu. It's pronounced just like the Pokemon, like Mewtwo. So it's mu, and the Greek letter mu, which is like a U, but you start from the bottom. And so it's like a U, but you start from the bottom, go up, and then make a U. And then that's not exactly as pretty as the typed one, so I'll erase it. So that's the population mean. It's often the number we don't know. Then, so the sample mean is an example of a sample statistic, and it's also a point estimate. So it's a sample statistic because it's one number that tells us something about a group, and it's a point estimate because it kind of tells us something about mu, the number we want to know but we don't know. The X bar is the point estimate. We can kind of estimate mu based on X bar. Okay, stacked dot plots is another way to do it. So instead of making them transparent, we just like drop them like little raindrops, but don't let them go side to side. So it's like Tetris. So if we drop them like that, then this is how one example of the different GPAs students could line up. Okay, so a histogram. So notice how this is easier to read than the other dot plot one, but it takes up more space. Okay, histograms. So histogram shows data density, even better than like a stacked bar plot. So they're convenient for describing the shape, and the bin width is arbitrary. It's something we decide. So for instance, it's kind of like a histogram. It's not a bar plot. Okay, it's like a bar plot, but it's when you have numerical data on the x-axis. A bar plot is when you have categorical data on the x-axis. So if on the x-axis here, it was like colors or names or something like that, then it would be a bar plot. But since it's numerical, it's a histogram. And with a histogram, you have to make a decision about how big your bins will be. So in our case, our bins go from multiples of 10. So bin width, we can do different bin widths. So for instance, I could just do bin width 50 up here, or 10, or 5, or 2. And they each tell different sorts of stories. So bin width of 10 and 5 tell the story of like decreasing a little bit. And then it's much messier with bin width 2. It's interesting how it peaks. So something interesting is that is really peaking around like 4 to 6, but then confusing is this part. It's hard to see the trend, whereas over here, the trend is easier to see. So it's bin width is a tricky thing. It's an art, not a science. So trying to figure out which bin width tells you the most about what's going on is something to try to look for. Okay, now let's talk about the shapes of a distribution. So here are a couple different things that a distribution could have. It could be, could have a single prominent peak, we would call that unimodal. Or it could have 2 peaks, that would be bimodal. Or it could have multiple peaks, and that would be multimodal. And then if it's roughly the same, we would call that uniform. So for instance, here, if you can kind of like the trend is like a unimodal, whereas the trend here is bimodal, and the trend here is multimodal, and the trend here is mostly uniform. Maybe you can make a case that it's unimodal, but it's maybe closer to being uniform. Okay, so to do this, to figure out if it's unimodal or bimodal or stuff, you want to like look for the trend, which again, like kind of like the histogram, like figuring out the bin width, is kind of an art form. So for instance, here on this first one, like with that, that just looks like I've got narrow bins. Like my bins are a little bit narrow. And if I had my bin width a little bit bigger, then I wouldn't see that probably. And so it'd still be roughly unimodal. Does that make sense? So whereas, you know, here on the third one, it really clearly goes way down and then up again. Okay. Moving on. Now, another way to describe the shape is the skewness. So by the way, in homework problems, when I ask you to describe the shape, I'm asking for unimodal or bimodal or multimodal or uniform. And I'm also asking for right skewed or left skewed or symmetric. So right skewed is when you have a tail to the right. Left skewed is when you have a tail to the left. And then symmetric is when it's the same roughly. Okay, so the skew is talking about like a tail going off to one side. All right, so to remember, right skewed has a tail going to the right, left skewed has a tail going to the left. Okay, and then outliers. So when you have a general trend of like going down, but then you have this guy there, that's a potential outlier. Okay, so finally, that's like our last thing to describe a distribution. Does it have potential outliers or does it not? All right, so here is a distribution of students who were surveyed about how many hours a week they spent on extracurricular activities. So how would you describe this distribution? So think about what we just talked about. Number of modes, left, right, or symmetric, and then potential outliers. Okay, so think about it, try to answer it on your own, and then I'm going to answer it in 3, 2, 1. So it's 1, unimodal, 2, right skewed, and 3 has unusual or potential outlier between 60 and 70. Okay, so modality, I'm going to kind of repeat some things. Unimodal, humps like that. Bimodal, 2 humps. Multimodal, 3 or more humps. Uniform, roughly the same. Then skewness, right skewed, left skewed. Remember, the skew refers to the tail that's going off to the side, and then symmetric. Okay. All right. Now let's do an example in thinking about how a distribution might look based on our common sense and knowledge of the world. So which of these variables do you expect to be uniformly distributed? Okay, so think back to uniform. So uniform right there. So would weights of adult females be uniformly distributed? Or salaries of random people from North Carolina? Or house prices? Or birthdays of classmates? Only one of them is going to be uniformly distributed. Okay, and the answer is D, birthdays of classmates. Now, why is that? It's because each day is roughly equally likely. But house prices, each dollar amount is not equally likely. And salaries of people, people tend to have, there's kind of a most common salary. And then there's like, it'd be right skewed because you'd have lots of people with really big salaries who are, but there's not that many of them. Okay. Now let's sketch the expected distributions of the following variables: number of piercings, scores on an exam, and IQ scores. So I'll do this first. So number of piercings, I would do, can't have any less than 0, but 0 would be the most common, and then no. So 0 is most common, and then 2, and then something like that. Or if I made like wider bins, like by grouping it by 2s, then something like that. Okay. What about scores on an exam? Well, let's say we're in a class, depends on like if there's grade inflation or not, right? So say we're in a class where there's some grade inflations. This is like 100. So then if we're dealing with a class of grade inflation, then it's going to be like that. Okay. Whereas if we're dealing with the class of not much grade inflation, it might be more like that. Okay. But probably unimodal, and probably still less skewed. You'd have people getting further away from, it's easier to get further away from the average if you're like doing really badly than if you're doing really awesome. So, and then IQ scores are intentionally pretty symmetric. Unimodal. Okay. So there's, the further away you get from the average IQ score, the less people there are that tend to have that score. All right. Now let's talk about variance. Now we're talking about measures of spread. Okay. So there's different ways of measuring spread. You do kind of like, in elementary school or middle school, you might have learned about like the range, stuff like that. That's not that useful though, but variance is. So this is a formula, and I'm going to break it down a little bit more. So the symbol right here, that symbol is the capital Greek sigma. That means sum. So summing from I equals 1 to n of xi means summing over all the different measurements, minus x bar. Remember, that's the average. So you take all of your measurements, subtract the average from each of them, and then square that, and then add all those squared numbers up, and then divide by n minus 1. So for instance, I think I have this in the wrong order. So here we have like hours of sleep, and x bar is 6.71, and there's 217 observations. Then to find the variance, you do, okay, well, one of my numbers is 5, one of them's 9, one of them's 7. So you take each number, subtract the average, square that, add up all the squared numbers, divide by 217 minus 1. Okay. So let me show you an example of this on like a Google Sheet. So like I said in one of the videos about R, I'll tend to use like R and R Studio for bigger things and spreadsheets for smaller things. So in this example, we'll use a spreadsheet to look at variance of something. So let's come up with some numbers. So let's randomly, so this will be X. So X will be 7, 3, 1, 2, 5, 6. Okay. So then over so I can label some things. And let's do like a total over here. So it's the sum of these guys. Okay. And maybe I'll do the average. Average of those guys, or the mean. Okay. So then, if that's the average, then what you do is you do X minus x bar. I'm going to do underscore bar to kind of mean like there's a bar over the x. Okay. Then, so that means you're doing equals, like that cell, minus the average. And I'll press F4. I'll press enter. And then, yeah, thank you, Google. I do want to do that. Okay. But I don't want these. Thanks. All right. So that means the average is 4. So 7 is 3 more than the average. 3 is 1 less than the average. 1 is 3 less than the average. 2 is 2 less than the average. 5 is 1 more than the average, so on and so forth. So then do x minus x bar squared. So then that means I'm doing this number, so the difference squared. Yep. So then 3 squared is 9, negative 1 squared is 1, and so on and so forth. Okay. And then that means that, so then I'm going to find total these. That's 28. Okay. And there's ID 1, 2, 3, 4, 5, 6. Okay. So there's 6 numbers. So then if I take equals that sum divided by 6 minus 1. So that means the variance of the numbers I just picked is 5.6. Okay. And so the spreadsheet, doing it this way helps you see like what's going on. So I've got numbers, and then I've got an average. I then look at like how did numbers differ from the average. So I subtract the average from each number. Then I square those numbers, add them up, and then divide by the number of numbers I have minus 1. Okay. So that is the variance. And then why do we use the squared calculation? So to get rid of negatives. So if I didn't square them, then adding up all the differences would just add up to 0. And I want to weigh larger deviations more heavily. So the standard deviation is then taking the square root of the variance. So then if I go over here and if I do standard deviation, that's equal to the square root of this one. So the standard deviation of my example is 2.366, taking square root of 5.6. Okay, and standard deviation, one reason to take the square root is because we squared all of these numbers, which means like say our x is measured in feet, then x minus the average is still measured in feet, but squaring it means we're in measurements of square feet now. So taking the square root gives us back to the original units, which is also helpful. Okay. So say we do the, going back to that our example of like the sleep thing, you know, s squared is like 4.7. So 4.11. So then the standard deviation is 2.03. Okay, so then think about a common thing is to have hardly any, or even like if you have a small enough sample, no observations that are within 3 standard deviations of the mean. So the mean is about 6 point something. And so 3 standard deviations of the mean would be past 0 or past like 12 or 13. So not all the data is within 3 standard deviations of the mean, which is normal. Okay, the median is if you put them in order, it's the middle one. And then if you have an even number of numbers, you average the 2 middle ones. Okay, so 0 through 4, the median is 2. You put them in order, 2 is the middle one. But 0 through 5, there's 2 middle ones, so average them up. Okay. Also known as the 50th percentile. Okay, because it's the mark where 50% of the population is less than that. Okay, so the 25th percentile is sometimes called Q1, and the 75th percentile is sometimes called Q3, and then the IQR, interquartile range, is Q3 minus Q1. And so the IQR is, instead of it being like the range of all the numbers, the IQR is the range of your middle 50% of the data, because it's going from the 75th percentile to the 25th percentile. Okay, and that's something we use when we do box plots. So when you do a box plot, this distance right here, what are you doing? This distance right here is the IQR. Okay, so that distance right there. When you do a box plot, the bold line is the median, and the other two lines of the box are the Q1 and Q3. And then this distance right here, in this case, it either is like kind of goes down to the bottom number, or it goes 1.5 times, right, times better, times IQR. And then anything beyond that, you kind of leave as dots, so that you can show some level of skewness or potential outliers. Okay, so this is, if you had put this horizontally, it would show you this is like right skewed data. There's a skewness, the numbers go higher, but not necessarily lower. Okay, and that's what this does right here. So if you couldn't read my handwriting, you can just look at this. So you've got the median is the bold line, Q1 and Q3. And so the distance from Q1 to Q3, that's the IQR. And then, so then you've got a max whisker and lower whisker, and then suspected outliers. Okay, whiskers of a box plot can extend up to 1.5 times the IQR. So, but if you run to the last thing, then you just make them shorter. So they can be shorter than that, but the max with maximum is 1.5 times the IQR. Okay, so say the IQR from here, Q1 is 10, Q3 is 20, so that means the IQR is 10. So then your max whisker reach is your Q3 plus 15, or Q1 minus 15. Okay, and then outliers are the numbers past that. Okay, why is it important to look for outliers? Well, they can help you identify extreme skew in the distribution. You can identify data collection or entry errors, and you can provide insight into interesting features of the data too. So for instance, here's the thing, my little video's in the way. Okay, that'd be right here. How would sample statistics such as mean, median, standard deviation, IQ, of household income be affected if the largest value was replaced with 10 million? So I don't know if you're familiar with this notation right here, but this notation right here means a 1 with 6 zeros after it. So 1 times 10 to the 6th. So 10 to the 6th would be a million. So we got some household income. So 2E05, that would be 200,000, 400,000, 600,000, 800,000, and a million. Okay. Noticing you got most of your people with wages below $200,000 a year. So if you took one of these dots, say like this one, and that person, say their business just takes off, and instead of making 1 million that year, they made 10 million. How does that affect some of our numbers? Well, let me get out of the way again. How does it affect the median and IQR are barely affected. So the median, with the original data, move largest to 10 million, move smallest to 10 million, it's still roughly 190, 200,000. And the IQR is still 200,000. It doesn't affect the IQR at all to move one number. But X bar, notice X bar gets like much bigger if you move the biggest, or even especially if you move the smallest one to be 10 million. And standard deviation gets gigantic if you move one person to getting 10 million instead of 1 million. So that means that we like to use mean and standard deviation when we can, but we prefer it when it's data symmetric and unimodal. If the data is not symmetric and unimodal, maybe use median and IQR instead. Okay, that's one of the lessons we're trying to learn here. So, all right, I'm in the way again. So median and IQR are more robust, meaning that robust means like they're not affected by one number moving around a lot. So for skewed, it's often best to use median and IQR. For symmetric, it's often better to use mean and standard deviation, because mean and standard deviation are taking in more information. So that's good as long as they're not being super affected by outliers. So if you'd like to estimate the typical household income for a student, would you be more interested in the mean or median income? So that depends on if student income is something you expect to be symmetric or if you expect it to be skewed. And I think a good guess would be that it would be skewed, because you could have a few students who have awesome jobs that are paying them much better than their fellow students, and it would be skewed to the right. So I think it's almost always when you're dealing with, oh dear. I just accidentally hit the power cord underneath my desk. So I think we're all good here. We can get back. Things are out of whack, but we're going back. Are we still recording? I'm going to pause recording. All right, we're back. So, and I think I'm recording the right screen, right? Yeah, okay. Yeah, so we're back. We're talking about robust statistics. And so if you were doing household income for a student, you want the median. Okay, now let's look at some things. So median versus mean. So if you have a symmetric distribution like this, then the median and the mean are the same. But if you have something that's right skewed, like here, then the skewness, it pulls the mean over. So the mean got pulled over by the skewness of the data. So right skewed, move the mean right. And here, left skewed, move the mean left. Okay? So right skewed pulls the mean to the right, so the mean is bigger than the median, and left skewed pulls the mean to the left, so the mean is less than the median. Okay? Okay, so which is most likely to be true for the distribution percentage of time actually spent taking notes in class versus Facebook or Twitter? So this is a fun study where there was a large lecture in a public university, and the professor asked the TAs, the teaching assistants, to sit in the back and count which students were like spending time taking notes and which ones were like goofing off, social media or whatever. And a lot of students were taking notes the whole time. Some students, not as much. So then we've got this distribution. So how would we describe this distribution? All right, think modal, left-right symmetric, and then outliers. So this is unimodal. There's one main mode. And then is it left skewed, right skewed, or symmetric? It is left skewed because the outliers, like the skewness, the tail goes to the left. So if the tail goes to the left, that means is pulling the mean to the left. So the mean is what compared to the median? It is less than the median. Okay, so in our example, the median is 80%, the mean is 76%. So it's pulling the mean. Those outliers are like the people who are studying basically nothing, taking like 0 notes in class. They're pulling the mean less than the median. Okay, when data are extremely skewed, then we might often do a transformation. So one example would be like a log transformation. So I'm going to show you 2 histograms. The one on the left is the number of basketball games that students attended at a university. And the one on the right is the log transformation. So that means we took everybody's number of basketball games they attended, we took log of that number. So then we end up with something that's a little bit easier to maybe understand as far as the trend, but it's harder to make a claim about like where things are. So for instance, like 70 games has like a log of 4.25, 50 games log of 3.91, 25 games is log of 3.22. By the way, this is natural log, not log base 10. So on a calculator, we're talking ln function, natural log. So it's hard to interpret these results, even if the trend is easier to see. Okay. So what other variables would you expect to be extremely skewed? Things involving money are always a good bet. So salary, housing prices, there's always like fewer things that cost more and a lot of things that cost less. So that makes them right skewed. All right, one last visual way of displaying data is what's called an intensity map or a heat map. So in this case, this is an example of like looking at how populations changed from one census to another. And so you have like the yellowish, and especially the dark yellow, means that the populations were going down. And then like light blue and especially dark blue means that the populations are going up. So you can see, for instance, like our area of Indiana, we're in northern Indiana, so we're in like light blue, but south of us, there's an area where it's populations going down. And a lot of this, the general trend that, you can see here is that rural areas are becoming even less populated, and cities tend to be more populated. And the things that are not like that are like just like North Carolina in general, Florida in general, Arizona in general. Those are just plain going up. So yeah, that's our last slide of section 2.1.